Hi everybody. In this video, I'm going to review with you the flame test lab that we did a few weeks ago. So what you did was you took these different compounds, these different chloride compounds, and you put a stick that was in water, and you touched it to the compound, and you put it in the flame, and it made all these pretty colors, right? And you say ooh and ah, but what does it actually mean? So we know that it's not the chloride part that's responsible for the colors, because we can see that only the first part of the compound, it's called the cation. Remember, cations are positively charged. The cation part is changing. That's the part of the compound that's responsible for all these different colors that you're seeing. If, we didn't do this experiment, but if you change the anion part, so the anion part is the second part here, that's kind of in purple color that I'm using, that's the anion part. In the anion part, if you changed it, nothing would happen. And I know we didn't do that experiment, but it's kind of one of the thought experiments that was in the post-lab questions for this lab. Nothing happens. That's why we didn't do it. It wouldn't have been very exciting for you to see. So what's actually going on here? So we know that the cation's responsible, but what's happening in the cation? Well, what's happening is the electrons are absorbing the energy. The electrons are found in their ground state. That's where their lowest energy state is. And when you add energy or pass electricity through the compound, the cation gets excited. It gets bumped to that higher energy level. So that's called its excited state. Heat or electricity does that. And then, because the electron can't maintain that excited state, you look here on the right, and the energy has to get released because you put energy in. So when the electron drops back down, the energy has to go somewhere. It comes out in the form of light. That's what a photon is. A photon is a packet of light energy. And the amount of energy that gets released is related to how big this drop is from the excited state to the ground state. And the electron can actually go to these different levels. The different electrons can go to different levels. And that's what we saw when we used a spectral tube. So on one of the days following the flame test lab, I got this spectral tube, and we put different compounds in there, in these discharge tubes, and electricity is passed through them. And then we used a viewer to be able to split that light into its components. And you see here, for example, hydrogen and neon have these bands. And each of these bands represents a special place where the electrons are being excited to, and then the electrons are going back to their ground state and releasing energy in the form of this light that you see. So even though you only see one light, one color here in the spectral tube, it's actually made of several different colors. And each of these bands represents an energy drop from the excited state to the ground state. Okay, so in the last part of this video, we're going to talk about the calculations that were required to do this lab. So if you have 680 nanometers of wavelength, right, for red light, what is the frequency and what is the energy? So you need to know the equations involved here. So the first one is C equals lambda nu. Lambda, as I already said, is the wavelength. And nu is the frequency. That's what we're going to solve for. And C is the speed of light. We already know the speed of light. We already know the wavelength. We have to find the frequency. So what you do is, you have your equation, And if I want to solve for this, I divide both sides by lambda to get lambda by itself. You see the lambdas actually cancel. So our equation is lambda equals c over nu. So I'm going to take this equation, and on the next page I'm just going to plug my values in. So just for simplicity's sake, I'm going to write the equation again. I'm going to plug my numbers in. We know that the speed of light is 3.0 times 10 to the 8th meters per second. We're going to use our that value will be given on the quizzes and the test. And our lambda is 680 nanometers. Now what we have to do with 600 nanometers is, since this unit is in meters, we have to make sure that the wavelength is also in meters. So we're going to turn 680 nanometers into scientific notation first. And then we're going to multiply times 10 to the negative 9, and that's how you go from nanometers to meters. So we're going to have meters here. We'll talk about conversions more in the second semester. 6.8 times 10 to the negative 7 meters. So that has to go here, where the wavelength goes. 6.8 times 10 to the negative 7 meters. And now we're going to do the calculation. So get my handy dandy calculator out. 3 times 10 to the 8th meters per second divided by 6.8 times 10 to the negative 7. And I'm going to turn that into scientific notation. And my answer is 4.4 times 10 to the 14. And see that the meters cancels the meters, so you're left with 1 over seconds. 1 over seconds is also known as hertz. So that's the answer for how you calculate the frequency from the wavelength. So the next thing the question asked us is to calculate the energy. So the equation for energy is E equals h nu. I can also use my previous equation depending on the information I've given. Now I just solved for nu, so I can plug into this equation, and h is Planck's constant, so I know I'm already given that on any test or on any problem. So I don't have to worry about memorizing anything related to the constants. You can also, if you didn't have the frequency, you can solve for frequency and plug that value in here, and you get the equation E equals hc over lambda. Now that's the way I'm going to do it, because when I solved for the frequency, I rounded it, and if I plug it in here, it's going to get rounded again. And when you round twice, you get kind of a different answer than you would expect. So, of course, in multiple choice, you just pick the one that is the closest to the one that you calculate. So, h here is 6.626 times 10 to the negative 34 joule seconds. C is 3.0 times 10 to the 8th meters per second. And lambda, as you see on the previous slide, is 6.8 times 10 to the negative 7 meters. You'll see here that the meters cancels the meters, the seconds cancels the seconds, and you're left with just the units of joules, which is what energy is. So now I'm going to type it into my calculator. Clear it. 6.626 times 10 to the negative 34 times 3 times 10 to the 8th meters per second divided by 6.8 times 10 to the negative 7. And now I'm going to, it's already in scientific notation. I'm going to write my answer down. And the answer is 2.9 times 10 to the negative 19. 2.9 times 10 to the negative 19 joules. And that's how you calculate energy from wavelength. Again, we could have plugged in our new value, our frequency value from the previous question, and we probably would have gotten a very similar answer. I just don't like to ever round twice when I'm getting one answer. So I hope that's helpful, and I will see you in class tomorrow to finish off the semester. Have a good night. Bye.